Hello everyone and welcome back. So now we're going to continue looking at the particle setup, and so far we have created two emitters, the particle separation and the particle edge, and now we're going to start looking at the particle sim itself. And I can start setting up the network and then run into the typical problems, but I'm going to tell you up front what they are and how I'm going to solve them. The main issue when we work with high-res destruction or high-res geometry is how we get collision, proper collision geometry. Now obviously we can feed in the entire geometry, the entire RBD setup, but with the resolution that we have, it's going to be a huge amount to we're going to waste a lot of computation power to read in that geometry and let the DOP create a collision geometry or collision SDF for that to interact with the particles. And the same problem happens with the geometry. So I'm going to show a method that I use to do collision with particles without having to use the geometry. And this is going to use volumes. So we're going to create volumes representation for everything, and we're going to create SDFs. So let's create a VDB from particles and fill interior, and let's use a fillet node to make sure that everything is filled here, and this geometry is packed. So let's unpack, and I'm going to set this to single polygon or probably triangles, and that's our SDF representation. Okay, so this is a volume now. And what we want to do as well is, let's put a trail node. We want to sample the velocity of this geometry. So let's compute the velocity, and then inside the VDB, we want to create a velocity field as well that we will use in a bit. So I'm going to add surface attribute here, point.v, and I'm going to call this vel. Now the best thing to do, I'll probably lower this a bit for now. The best thing to do is to write this to disk, because we don't want to recompute this every frame. Now remember that when we write this to disk, it's going to write every frame. And if we use multiple substeps inside the DOP network, we're not going to have in between frames. So you have to be very careful when you use if you cache this to disk. You have to make sure that you're going to use one, or just one. And then if you need more, it's best to keep this geometry live and pay for the overhead of creating the SDF every frame. So that's something to keep in mind. But for now, we're going to be able to create the particle sim with just one. Cool. So let's say we have some particles. So I'm going to create a bound around this, and let's time shift. And let's say we have this geometry. I'm going to fill it with points. So VDB from polygons. I'm going to create a volume. Set this to 1, and then I'm going to scatter a lot of points. I don't need relaxation, and let's increase this more. And what happens with the collision with the particles is every frame the particle would check. If we have, for example, a particle falling in onto Kong and interacting, the particle would check if they entered the volume of the whatever geometry we have. If they did, then they will go back and fix themselves by pushing the point back into the ISO surface. So that's what happens inside the POP network, and we're going to do something similar. So what I want to do now is I want to take all the points that are inside the overlaps with Kong and push them outside, so there is nothing left inside the volume. Okay, so I'm going to do this using point VOP and volume samples. Okay. So first of all, we want to find if the point is inside the volume, and we're going to do that by sampling the surface field. So I'm going to use a volume sample the input for the volume is the second input, and I prefer to use the name. So the name of the field is surface, and that's what we called it here. So that's what we are going to sample. We can use the name, the number, and that's going to be number 0 because it's 0 here. So the first one 0, second one is 1, and so on and so forth. So let's set this to second input, name, surface, and then the sample position is the point position itself. Now let's plug this into the color, and right away you can see we have white information here and black when the points are inside the volume. So we know something. Okay, let's take a look at the values, at the color value. See, it's 0.6 and then it's negative. So everything else here below 0 is when things are inside the volume. So what we're going to do is we're going to use a compare node. And we're going to say if it's less than 0, we want to do something. If it's greater than 0, we want to do something else. So we have that compare. We're going to plug it into a two-way switch. I'm going to use two constant, red and blue. So red here, and if it's not true, I'm going to use blue, and let's plug this into the color. And there we go. We now know the points that are inside the volume and the points that are outside. The points that are outside, we don't want to touch them. We don't want to change anything. We just want to operate on the points that are inside the volume. Okay, so we know them. What can we do with them? Well, when we create the SDF, it knows. Let me do this. Let me do a VDB from Polygon. VDB convert. I'm going to convert this into a polygon. So you see this isosurface here. If I shrink it, if I scale it down, you see it's going to go in the negative range. And then if we scale it up, it's going to go to a certain point and then stop because there is no more information. But in the negative, it's going to go all the way in. See? So the way this is happening is these voxels, they know how far they are inside the volume. Okay, so this is allowing us to go deep all the way inside the volume to the deepest point, and then we can go up back again. And 0 is where the isosurface is the limit of the isosurface. So what can we do with this? Well, if we know how we can go in and out, it's like having a geometry normal. So if I go here and use a peak node, what the peak node does, it computes, I'm going to compute the normals. The peak node pushes the points along the normal. So we have a vector. If this is happening, we have a vector that this SDF knows about, and that vector is called the gradient. What the gradient is it's basically the distance or the shortest vector that will take that voxel back into the isosurface. Okay, and that's going to give us somewhat similar information to what the normal of a surface looks like. So let's go back inside, and we're going to use a different node now because we want to read in this gradient information, and that node is called volume gradient. What this node likes is it likes to work with SDF, so we have to provide a surface field. So let's connect the sample point, and we're going to say it's the second input, and the name is going to be a surface. It's not going to read the field itself, but it's going to read it and compute the gradient. So let me plug this into the color, and we'll see that we have black everywhere where there is no information about these normals, and probably there is some bits here, and then it's colored inside. So why is that? Well, that's happening because there is data there. There's normal data. So if we connect this into the normal and then view the normal information, we will see that there is actual direction. Okay, you see here it's pointing in the right orientation. and that's the information we're going to use to push the points back. Now this is only a normal information, it's not telling us anything else. Well, it is, but we're gonna normalize it, okay? And that's gonna set everything, all the normals, all the vectors to a length of 1. So this bits give us the angle or the direction that this point needs to travel along to get to the isosurface. But how much do we need to push the point is something that's coming from the surface field. So the compare here, remember, if you guys remember, it has a negative value, and that value is what we're going to use to push the points back. Okay, so for now I'm not going to change anything, but I'm going to use this I'm going to leave this vector for now, and then I'm going to add it to the points. So we're basically offsetting all the points by this information, okay? And then I'm going to either use push them or keep the original position using this, and then I'm going to plug this back into B, and you can see they snapped back, they snapped outside. It's not enough to push them all the way to the isosurface, but they snapped and moved along that direction. Okay, now let me copy this as well. I'm gonna add the colors again. So you see, let me hide the normals. See the red points? If I disable this, see they're inside, and what I'm gonna do is I'm gonna increase the number of points and delete anything that is not red. Okay, so this is the points inside the volume. We haven't pushed them yet, so let's do that and see. Now they are pushed a certain amount from the along that angle, but this amount is not perfect. So in the next video we're gonna set it so that we are going to push all the points the amount needed so that they are outside whatever volume they were in, and that way we're going to place them all at this isosurface. And this is the technique that we're going to use in DOPS to have the particle to give the particle a proper collision system. So we'll continue that in the next video. Thank you guys for watching, and see you in a bit.